Hello everyone. So today we're going to go over section 1.1, 4 ways to represent a function. So here we have the definition of a function, a relation between a set of inputs in the domain and the set of potential outputs in the codomain, and the set of actual outputs is called the range. Important property of the function is that each input must map to one output only, even though different inputs can map to the same output. And we'll see this in the arrow diagrams below. So first we have f of x is equal to positive or negative x. So let's say x is equal to 1. Then we have two different values in the range. It could be positive 1 or negative 1. So this makes it not a function and just a relation between the domain and the range. Second, we have f of x equals to x minus 1. So for example, we can have x equals 1, 2, and 3. And of course, 1 minus 1 gives us 0, 2 minus 1 gives us 1, and 3 minus 1 gives us 2. This is a function, and it's known as a one-to-one function since each element in the domain maps to a different element in the range. Finally, we have f of x equals to x squared. So let's say, for example, we have 1, negative 1, 2, and negative 2. And of course, both negative 1 and 1 squared gives us 1. Both 2 and negative 2 squared gives us 4. Now this is still a function since each element of the domain maps to only one element in the range, but it is not one-to-one. It's a many-to-one function. So as a quick additional example of an arrow diagram, here we have f of x equals to 2x plus 1. So of course 2 times 1 is 4. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, and then plus 1 is 7. And we can complete the arrow diagram this way. Next, we're going to look at the 4 different ways to represent a function. We can describe a function in words. We can use a table of values. We have a graph. And finally, we can use an equation or formula to describe a function. In this case, we have the graph on the right-hand side is actually verbally a number squared, and then we subtract 1. Nope, sorry about that. We can also make a table of values for this. X and y values. So let's say if x was negative 2, negative 2 squared is 4, 4 minus 1 is 3. And then we can have negative 1 squared is 1, minus 1 is 0. 0 squared is 0, minus 1 is negative 1, and so forth. So a small table of values. Sorry about that. Okay, visually we have a graph, and finally algebraically, this function would be written as f of x is equal to x squared minus 1. Let's continue by looking at domain and range. So as we know, the domain is the set of inputs. So this is the mapping from here. And the range is the set of outputs, and this is the mapping to. So here we have the blue graph of a function, and we're going to look at its domain and range. So the domain, let's say here we have the values a and b, and for the range we have the values c and d. So the domain of this function would just be from a to b. Notice the open circle where b is, so that means the boundary value of b is not included in our domain, and we're going to use parenthesis to indicate that it is not included. Whereas on the left hand side, where a is, that's a closed circle, so a is included in our domain, and we use a square bracket for that one. The range is from c to d, and both those boundary values are included. Okay, so next we're going to look at domain and how domain restrictions work just a little bit. In our first example, we have y equals to the square root of f of x, and that means that f of x must be greater than or equal to 0, whatever f of x happens to be. On the second example, we have y is equal to f of x over g of x. Now, since g of x is in the denominator, g of x cannot be equal to 0. So those are generally the kind of restrictions on the domain that we've been looking at for functions. Okay, let's try these out. For our first example, we have f of x is equal to 2x plus 3 over x squared minus 4. Now, since x squared minus 4 is in the denominator, it cannot be equal to 0. Okay, which means if we factor the left-hand side, we have x minus 2x plus 2, which cannot be equal to 0, which means that x cannot be equal to positive or negative 2. Alternatively, we could have also just moved 4 to the right-hand side, and then just square root both sides, and we still get x cannot be equal to positive or negative 2. Okay, in the next example, we have, well, two parts. Number one, x squared plus 3x plus 2 is underneath a square root sign, so it must be greater than or equal to 0. Okay. Now, on the other hand, since square root of x squared plus 3x plus 2 is in the denominator, we know that x squared plus 3x plus 2 cannot be equal to 0. So we can actually combine these two restrictions into just x squared plus 3x plus 2 must be greater than 0. Okay. So that's the combination of these two restrictions. So from there, we can, of course, factor the trinomial. We get x plus 2 and x plus 1 greater than 0. Considering the associated equation, we have two roots, -1 and -2, which means the number line will be cut into three parts from negative infinity to -2, from -2 to -1, and finally from -1 to infinity. And we can test each interval by choosing numbers in those intervals. So for example, we can test here x is -3. Here we can test x is equal to -3/2, for example. And here we can test x equals 0. And after doing so, by substituting -3 into our inequality, that actually holds true. The second part does not. And finally, if we let x equal 0, we have 2 times 1, and of course 2 times 1 is greater than 0, so that is part of our solution as well for the domain. So ultimately then, the domain of this function is going to be x is either from -infinity to -2 or from -1 to infinity, but not the numbers in between. Okay, let's look at example C. So here we have two square roots. The first square root tells us that x must be greater than or equal to 0. The second square root tells us that 4 minus x must be greater than or equal to 0. Now, if we were to move x to the right-hand side, we have 4 is greater than or equal to x, or just x is less than or equal to 4. Combining the two different restrictions, we have the domain, and that is x is between 0 and 4. Or written as an inequality, 0 is less than or equal to x, which is less than or equal to 4. So next we have piecewise functions. And these are functions that are defined by different rules for different values in the domain. So in our first example, f of x is equal to x if x is less than or equal to 0. We can go ahead and graph that. It's right here. So we'll use an arrow on one side to indicate that the line keeps going. And on the other side, we're going to use a closed circle to indicate that the graph stops there. Now, once x is greater than 0, the function changes to 1/2 x plus 2. So here we're going to use an open circle at the y-intercept of 2. And then from there, we have a slope of positive 1/2, which means the rest of the graph will look like this. And that's how we graph a piecewise function. Notice that the domain for this function is all real numbers. Sorry, x is an element of the real numbers, since all x values were covered. The range, on the other hand, actually goes from -infinity to 0, and then from 2 to infinity. So here we have -infinity to 0, including 0, so we use a square bracket there, or from 2 to infinity. Notice that 2 is not included in the second interval. Let's move on to example B. So here we have 4 minus x as our first part, from -infinity to 1. Okay, so let's see what that would look like. something like this. Right, the slope is -1 and the y-intercept is 4. And we're going to include the value here since it says x is less than or equal to 1. And after that, when x is between 1 and 3, excluding 1, we have x squared. So it would just be 1, 1, 2, 4, and finally 3, 9. So we have a curve, part of a parabola that looks like this. For the second part of the function, we're going to include the value at the top there. And finally, when x is greater than 3, we simply have -6. So here's -6, open circle, and horizontal line at -6. The range of this function first part is just the individual value of -6 on one side, and then on the other side is actually from 1 to infinity, excluding 1, because of the open circle here. Okay, so that's for piecewise function. Let's look at odd and even functions next. So the property for even functions is that f of -x is equal to f of x. Odd functions, on the other hand, f of -x is equal to -f of x. An example for even function would just be the absolute value function. So something like this. And this is an example. Notice that if we substitute, let's say, for example, -5, the absolute value of -5 is 5, which means we have this kind of symmetry here. So this even function exhibits line symmetry about the y-axis. Okay, so for an odd function, we simply have y is equal to x. Right, so let's say, for example, if we substitute in -5, we simply get, well, -5. So this exhibits rotational symmetry of order 2. And that's 180 degrees. This is about the origin. So that's kind of the definition of odd and even functions and a couple of quick examples. Now, for the next part, we're going to look at some different functions and try to determine whether they're odd, even, or neither. So how this works is we're simply going to find out what f of -x is for each function. So here we have -x to the 5th power plus -x. Expanding this gives us -x to the 5th power minus x. From there, we can factor out the negative. So we have negative and then multiply by x to the 5th power plus x, which of course looks like the original function. So this is simply negative f of x, which means our first function is odd. Let's move on to the second one. So here we can find out what g of negative x is. So 1 minus 2 negative x to the 4th power. Negative x to the 4th power, of course, that's an even power. So we just have 1 minus 2 x to the 4th power, which of course is just g of x. And that will make this function even. And finally, the last example in example 4. So h of negative x is equal to 2 times negative x minus 3 times negative x squared. So of course that will give us negative 2x minus 3x squared, which cannot really be made to look like h of x multiplied by a negative sign, or even just h of x by itself. So this is actually neither odd nor even. So one last part is about the difference quotient. This is an example that we've seen before. So we have an f of x, which is just 2 minus x squared. We're going to find out what f of a plus h minus f of a all over h is. And again, this will be covered in greater detail in a later chapter. So it's a quick example about how this works. So substitution, 2 minus, and then a plus h squared minus, we're going to use parentheses here, 2 minus a squared. And this will be all over h. Okay, from there, we're going to expand the trinomial, so we get a squared plus 2ah plus h squared, and then minus 2 plus a squared, after using the distributive property there. Okay, now we're going to try to also apply the distributive property in the middle part of the numerator. So we get 2 minus a squared minus 2ah minus h squared minus 2 plus a squared all over, again, h. Notice that we have some equal and opposite terms here. We have 2 and negative 2. We have negative a squared and a squared, so those will be eliminated. So let's continue to the right-hand side here. We now have negative ah minus h squared all over h. We can factor out negative h from here. Be left with 2a plus h. And then this, of course, is all over just h. And the h's will be eliminated as well. And finally, we're left with just negative 2a plus h. Or, alternatively, negative 2a minus h. And that's it. So we looked at definition of function, the 4 ways of representing a function, domain and range, piecewise function, odd and even function, and finally the difference quotient today. So that's it for today. Once again, thank you for listening.